Hello and welcome to Otten Math. In this edition of Otten Math, we're going to talk about complex numbers. We got a lot of stuff to cover, a lot of work to do, so let's move on. All right, so just some refreshing for you. Standard form for a quadratic equation. Y is equal to ax squared plus bx plus c. So in this case, a would be 3, b would be 4, and c is 7. So a, b, and c, a and b represent the coefficients in front of x squared and x respectively, and c is the constant in the standard form. All right, so I want you to take a moment to factor this quadratic. I'm going to pause here. All right, you should end up with y is equal to x minus 3 times x minus 1. Now, can you just quickly graph or sketch a rough graph of the quadratic function? All right, you should end up with a parabola that faces up. And it has 2 points where it crosses the x-axis. Both at 3, 1 and 3, 0 and 1, 0. All right, so now can you tell me where the graph crosses the x-axis, which I just did? So 1, 0 and 3, 0 are the two coordinates where the graph crosses the x-axis. All right, so the last thing I want you to do is tell me what the roots, zeros, or solutions are. And the reason why I ask you this is I want to distinguish between quadratic factors, x-intercepts, and then also roots, zeros, and solutions of the quadratic. So in this case, the roots, zeros, or solutions would be x is equal to 3 or 1. So basically, it's telling me where the graph crosses the x-axis, providing the x value. Here is the coordinate value, and here are the quadratic factors. So in a test, or if I have a homework problem for you, if I ask you to solve, then you would provide me with x is equal to some value. If I asked you to factor, then you'd provide me with these two quadratic factors. And if I asked you to provide me where the graph crossed the x-axis, you'd provide me with these two coordinates. All right, next question. Can you factor this quadratic? I'm going to pause for a moment. All right, so you're going to need to use a quadratic formula in order to factor. You could say it's not factorable with an integer value in the quadratic factor, but you can use the quadratic formula to solve the quadratic equation, then to use that value as the intercept to write a quadratic factor. So if you use the quadratic formula, you'll end up with minus 1 plus or minus I root 2. And then you can use that for your factor, or your two factors. So x minus 1 plus or minus I root 2 would be your factors. Now, what are the roots, zeros, or solutions? So we use the quadratic formula in order to find the roots, zeros, or solutions. So we just replace the value that we had determined with the quadratic formula, and I'm just going to write in here x is equal to, and where does the graph cross the x-axis? And the answer to that is it doesn't, right? So we have a situation where the graph faces up or down, in this case up, and the graph would now be above the x-axis. It would not touch the x-axis, so there would be no real solutions, just two imaginary solutions to the problem. All right, so that's where complex numbers step in. So we have our 6 different possibilities: faces up or down, doesn't touch the x-axis, 2 imaginary solutions, touches the x-axis once, so 1 real solution, or crosses the x-axis twice, and in that case I have 2 real solutions. All right, this is just another example. All right, so imaginary number is defined as, we kind of already alluded to imaginary numbers. I'm assuming that you have some experience with them, but let's review imaginary numbers again. Imaginary number is defined as the square root of negative 1. We can abbreviate that with a lowercase I. All right, so now when simplifying radicals that have a radicand that has a negative value, what we want to do is to break out as a factor, the square root of negative 1 as I, and then solve having removed the factor of negative 1 from the radicand. So as an example, square root of negative 7 becomes the square root of negative 1 times the square root of 7. Square root of negative 1 we had identified as I, so the answer is I root 7. And so this is the process that I want you to go through when evaluating and simplifying the square root of a negative value. I want you to remove or factor out square root of negative 1 from the radicand, rewrite using your properties of radicals, and then simplify the square root of negative 1 as I. All right, so I want you to handle the next two, and I'm going to pause for a moment. All right, so the next one, you'll get square root of negative 1 times 9, which is the same as 3i. Second, square root of negative 1 times the square root of 4 times the square root of 3. Square root of 4 is a perfect square, so this becomes I, 2i root 3. Okay, moving on. Operations with imaginary numbers. So I to the first, I squared, I cubed, and I fourth. Let's see if you can take a moment and fill out what the values are for the first column on the left. I'll come back and show them to you. All right, so in the first column on the left, of course, I to the first power is just square root of negative 1. I squared would be the square root of negative 1 times the square root of negative 1, which is negative 1. I cubed, which would be negative 1 times the square root of negative 1, which is negative 1 times I, which is just negative I. And then I to the fourth would be the same as I squared times I squared, which is negative 1 times negative 1, which is 1. So as you evaluate the balance of the values that I'm asking you to simplify, you'd end up with a pattern: square root of negative 1, negative 1, negative I, 1. Square root of negative 1, negative 1, negative I, 1. And then again, square root of negative 1, negative 1, negative I, 1. All right, so you can see that this pattern repeats itself every fourth integer value for the exponent. And so if you're confronted with a situation where you need to evaluate some value for I with an integer that's a large integer, you would just then divide by 4 and find out what the remainder is. And then if the remainder is 1, then your value would be the square root of negative 1. If it's I squared, it would be negative 1. If it was I cubed, negative I, and then I to the fourth would be just 1. All right, so let's take an example. What is the value of I to the 752nd power? And if you evaluate that by dividing by 4, you'll end up with an integer result. So you end up with 1. So I believe that, if I'm not mistaken, 752 divided by 4 is equal to 188. So there's no remainder value, and your answer would just be 1. So you'd correspond that to I to the fourth. All right. You can also try what's the value of I to the 1753rd. I divide by 4, 438 with a remainder of 1. If I evaluate remainder of 1, again, I see that remainder of 1 is equal to I to the first power, which is just I, or the square root of negative 1. All right, so let's go through the process of multiplying, dividing, adding, and subtracting, which will multiply first, square root of negative 3 times the square root of negative 3. All right, and if you adhere to the process that I've asked you to adhere to, removing as a factor square root of negative 1 from each of the radicand values and then multiplying, you end up with I root 3 times I root 3, which is I squared root 9. I squared is negative 1 times the square root of 9, 3, and you end up with negative 3 as the value. Okay, next, square root of negative 12 times the square root of negative 3. You end up with 2i, and I prefer that the integer value is placed before the I. 2i root 3 divided by I root 3. I over I is 1. Root 3 over root 3 is 1. So you end up with 1 times 2 times 1, which is 2. All right, simplify these. We'll come back. All right, so again, this becomes I root 2 times I root 5, which is negative 1 times root 10. Second, 5i, perfect square 25, 5i root 2, so you end up with 1 over root 2. Then you have to reposition the problem by rationalizing the denominator, multiplying both the numerator and denominator by the square root of 2. Square root of 2 over square root of 2 times 2 is square root of 2 over 2. And that's your answer for B. All right, so I want you now to add and subtract these values. I'm going to pause here. All right, so square root of negative 4, 2i, plus 4i plus I is equal to 7i. Square root of negative 49, 7i, minus 3i, minus 6i is equal to negative 2i. And we treat I like a variable x or y. So if you have 2I plus 4, it would just be 2I plus 4. If it was 2I plus 4 plus 4I plus 1, it would be 6I plus 1. So like terms we combine. Like terms include values with I. So 2I plus 4I plus I, all like terms, we can combine them, 7I. But a constant value we would not be able to combine or add into the values also with I. And the second, 7I minus 3I minus 6I ends up being negative 2I. All right, so let's talk about complex numbers now. Complex numbers, and this is, we're getting into the meat of the presentation. Complex numbers includes both a real and imaginary part. It's written as A plus or minus BI. So real part 3, imaginary part BI or 4I, 3 plus 4I. In order for this to be a complex number, this value 4, which we'll call B, has to be some integer value, cannot be 0. So in this case, we have a complex number. Now, if this value, the real number, is 0, then we call this 4I a pure imaginary number. All right, so complex numbers involve both a real and imaginary part. You need the imaginary part to have the complex number, otherwise you just have a real number value. All right, so let's add and subtract. All right, there's a lot going on in this slide, but adding and subtracting, again, is very simple. We're going to add the like terms together. Like terms would be the real number values and separated from those real number values, your imaginary values. So 3 here and 6 would be the real number values. 4I and 7I are your imaginary values. So you'd add them independently. 3 plus 6 is 9. 4I plus 7I is 11I. All right, where things get mildly complicated is when you're subtracting complex numbers from each other. You have to recall that a representation of a complex number typically is in parentheses. You subtract them from each other, and you'd end up with a quantity C plus DI subtracted from A plus BI. But you have to remember now that you are distributing that negative value, so it becomes A minus C plus BI minus DI. And so remember to distribute the negative sign when you're doing the subtracting. For the second example here, 3 minus 4I minus 2 minus 6I ends up being 3 minus 2 minus 4I plus 6I, which is 1 plus 2I. All right, I'm going to allow you to do these on your own. I'm going to give you a moment, and then I'm going to come back and show you the answer. All right, so these are the answers. Again, distributing the bottom, combining like terms, simplifying. All right, so multiplying and dividing. Multiplying, getting to be a little bit more challenging here. We're going to just FOIL when multiplying complex numbers. 4 times 3, 4 times negative 2I, plus 5I times 3, plus 5I times negative 2I, and then combining like terms. The only challenge here comes negative 10I squared. I squared is negative 1, so negative 10 times negative 1 is 10. So we're actually adding 10 to 12, not subtracting that value. So this ends up being 22 plus 7I. All right, so I'm going to allow you to take care of this, and I'm going to come back. All right, so you should end up with these values 37 and 31 minus 34I. Cool thing about this is with the difference of two scores, we end up with only an integer value with a real number. And we're going to use that concept of the difference of two squares in order to rationalize denominators with a complex number. I say division is a little bit more complex for complex numbers. When you divide by a complex number, you have to rationalize the denominator, and you rationalize by multiplying by the conjugate of the denominator. So let's go through. You can read this here. You can pause it, and I'm going to go through a couple problems, and then we'll be done. All right, so by order of the math gods, they say math gods, we can't have complex numbers in the denominator, so we need to multiply by a conjugate. Conjugate of 3 plus 3i is 3 minus 3i. So we're going to multiply by the conjugate over itself, which is just 1. So we're not changing the value of this original term. We're just rewriting it. Right, so 3 times 3 minus 3i is 9 minus 9i. 3 plus 3i, we FOILed 9 minus 9i squared, which is 9 plus 9. I end up with 9 minus 9i over 18. And then further simplifying, removing the greatest common factor. In each of the terms, I end up with 1 minus I over 2. So let's give you a couple problems to solve on your own. Again, I mentioned the difference of two squares. Here's your first problem. I'm going to pause. I'm going to show you the answer. All right, multiplying by the conjugate of the denominator, 3 plus 6i over 5. Next one, 1 over 4 minus 3i. And here's your answer. That's it for this edition of Hot Math. Only have 15 minutes. Talk to you next time.